Woo. Okay. Yesterday we left off talking about rate of change problems. These are problems where we focus specifically on how a function is changing with respect to time rather than one of the individual known variables. So taking a derivative not with x or with y, but with this unknown quantity t. And for homework problems, every problem fits in this category. You could take a function where you have a setup where we have, oh my gosh, my brain's stopping while I'm trying to work. No, brain. Okay. We could have a function where we're dealing with just x values, so we could ask for the rate of change of x, so d dx. We could ask for the change in y, so d dy. We could ask the change of t, d dt. And in these functions, as we go through them, there'll often be some known quantity about them, some change that is known. So like the x is changing in a specific way, the y is changing in a specific way. So dx dt is known, dy dt is known. We just have to be able to take that information and present it into the problem itself. For today, I want to focus more on these word problems. These word problems can get interesting. Let's start looking at number 12. Find the rate of change of the distance between the origin and a moving point on the graph of y equals sine of x if dx dt is equal to 2 centimeters per second. So there are a couple of basic steps that are considered to be standard in these kinds of problems. And you'll notice that for some of these, they look kind of like physics steps. So step 1, it is often beneficial, if possible, to draw that picture. Step 2, list any known or possibly needed formulas. What do I mean by this? Keywords and phrases: area, surface area, volume, distance. These are formulas that are known. These are formulas that are mathematically findable. Ones that either we need to have memorized or ones we could quickly look up if we needed to. And so if it mentions any of those terms or any other terms that come from mathematics, we need to have those formulas readily available to us. Step 3, we need to set up some kind of equation. Using the picture, using the list of known equations to set up something new, something specific to this particular equation itself. Here we go. Let's start with number 12. 12 says, find the rate of change of the distance between the origin and a moving point on the graph of y equals sine of x if dx dt is equal to 2. So let's list some things out. First, I'm going to start with my picture. From trig, standard sine function. Ooh, it's beautiful. I know. I've been practicing. We have pi over 2. We have pi. We have 3 pi over 2. We have 2 pi. And so what we're talking about here is what's happening to the distance at any point in time between a point on this grid and the origin, which I'm going to label as d for distance. So as you can see, if I'm following this path, this distance is going to change based upon the angle this point makes with the ground, thereby creating a distance formula. Now, first picture. Yeah. 2, known or needed formulas. Well, I got 1 in the equation. Y equals x squared plus 1. Okay. Thank you. I'm looking at 11 because we were talking about 11 yesterday. Sine of x. Okay. If dx dt is equal to 2, so we know dx dt is equal to 2. So one equation which represents the function, one equation that represents some part of the function's derivative, dx dt. But it actually mentions something more specific in the problem itself. It says distance. So now you get to pull out the distance formula. This distance is calculated by a simple formula referred to as Pythagorean's theorem, which states that the square root of, so in standard notation, x2 minus x1 plus y2 minus y1 and square rooted. The standard distance formula. Now, a few things that are really neat about this problem. We also know from the problem that this is the distance from the origin. which means some of these numbers are knowns. In this case, one of our x's and one of our y's will always be 0. Meaning I can modify this formula a little bit. If I assume the x1 and the y1 are the zeros, x2 minus 0 would be 0. Square that would just be the x value squared. Same with the y value. So our function, distance, is equal to the square root of x squared plus y squared. Now, what's the question asked me to find? It asks to find the rate of change of the distance. So how is distance changing? D dt. How the distance is changing. In other words, the y is going to change with respect to time. The x is going to change with respect to time in the right order, hopefully. They're going to change with respect to time specifically, allowing us to take a new function. But there's one problem. I want to find this change, d. I know dx dt. If I take the derivative right now, I'm in trouble because I have two variables. So I end up with dx dt and dy dt. I don't know what dy dt is. I have no idea what dy dt is. Thankfully, in my hand-dating bag of algebra tricks, other one, substitution. I know from this formula that y is equal to sine of x. So what can I do? Anywhere there's a y value, I can replace with sine of x. My new distance formula. The distance, d, is equal to the square root of x squared plus sine squared of x. Now, looking ahead, if I take the derivative, on the left-hand side, I will end up with the rate of change of the distance, which is what I want. The second thing we'll end up with, on the right-hand side, I'll have to do a chain rule of some kind with a square on the outside, but inside, I will only end up with changing x's, which I have as a known value dx dt. This is actually perfect. Common steps in these kinds of problems is to make a substitution to remove one of the variables. Not done every time, but common. So, let's now take a look at this problem using the steps we talked about yesterday. We have the following equation. D is equal to the square root of x squared plus sine of x.
James, you got a copy?
Don't love you. I'm going to use my standard identities from algebra to convert this into power rule. 1/2 power. I'm even going to use one of my shortcuts for the derivative rules to find this derivative a little faster even. But now I need to do this. I'm taking the derivative with respect to t of both sides. So on the left-hand side, this will look a little strange. That's why oftentimes they'll use, instead of d, they'll use the delta symbol. The delta symbol looks very similar to d. It looks like an unfinished backward 6. This says delta d over delta x, or in this case delta t. That way you don't think d times d is d squared or something weird. One is a d, one is a delta. Find a way you can move rid of the t's and the r's. Okay, on the right-hand side, I have to do a power rule problem with a chain inside of it. So I can either use the standard power rules of the chain, or I can use the little shortcut we talked about using u and u primes. Either way, I should be able to get the derivative of this function. Let's walk through one step at a time. First thing I'm going to do here. Take a derivative. Power, right? 1/2. Maybe they're the same. Subtract the power by 1. Then down through to the inside, in parentheses. What is derivative of x squared? But since we're doing it with respect to t, it'd be 2x dx dt. Plus, what is the derivative of sine squared? So that's a power rule. The square has to be dealt with first. So the 2 is going to move out front. Remember with the power rule, the inside stays the same. So it becomes 2 sine. Subtract 1 from the power, make this the first power. Times cosine, because that's the derivative of sine. Times the derivative of what's inside cosine. Inside of cosine is x. Derivative of x would be dx dt. So, this big, beautiful equation, that is the rate of change with respect to the distance. Okay, last thing it told us to do. In the problem, it tells us specifically dx dt is equal to 2. Average dx dt, we replace it with a 2. So dx dt right there is now 2. Right there is now 2. There's nothing else to fix, so this is actually going to be fine. Delta t, delta t, delta d, delta t is equal to, the 1/2 stays out front for now. X squared plus sine squared x. We haven't changed that any because there's no delta t's or delta x over delta t in there. Right hand side, 4x plus 4 sine x cosine x. Okay. I'm going to algebraic simplify a little bit here, but not much. To start with, let's see, negative power should go in the denominator. So on top, let's actually just talk about this piece. I have a 1/2 here, 4 and 4. Pull out a 4, multiply by 1/2 to the 2. So that means I end up with a 2 on top. If I pulled it out, what's left behind would be x and sine x cosine x. On bottom, the negative power is going to go to the bottom. The 1/2 power. And we could convert that 1/2 power back into a square root, but either way, both solutions are considered acceptable. This is the rate of change of the distance to that particular spot in the function. Notice we did it. We had to plug into the distance formula to take that function. And take that function, we had to figure out how to find that function in terms of a single variable for this particular problem. But for other problems, we do have the ability to do dy dt and dx dt separately. So this one specifically asks the rate of change of the distance, d dt, is the correct solution. In fact, as a function is good, because now it's a function with respect to x. Meaning if I want to know what's happening at 3 pi over 4, I just take the x value, plug it into this function, and we can see how the distance is changing with respect to time. This kind of mathematics is actually done by things like radar guns. They write a computer program that does it for them, but the idea is the same. If, for example, you have a car going in front of you, it has to figure out how the rate of change is going from a different place, from a different fixed point. And so you have a fixed point over here, and this car moving away from it. It can use the derivative rules of the computer program to figure out exactly how fast the car is going, even though you're next to it instead of behind it. It's a pretty neat thing. Questions? So, on these kinds of problems, note the process. The picture part is not required, but it can help you determine the formulas you may need and the equation you want to get, which is why it's recommended. Look for key words and phrases in the problems themselves to help lead you to which functions, which equation you're supposed to use. Like I said, any equation from geometry, algebra 1, algebra 2, trig, and anything in calculus we've talked about so far. They're all fair game. Note some terminology in the problem itself. Right here. That leads you in this direction. So let's analyze the problem itself. It says right here, first part of the problem. The rate of change of the distance. This is delta d over delta t. It mentions distance. That means they're going to use a distance formula. The origin was used to help part of the distance formula be simplified along this graph. where I have some known dx dt is equal to 2. That's it. Part of this class now becomes the ability to take this function and read it differently, so that you can figure out how to find those components. Okay. Next problem. Okay. Looking forward to. Let A be the area of a circle of radius r that is changing with respect to time. If the r dt is constant, is the a dt constant? Explain. Okay. Let's break this one down. There's going to be relatively little math in this problem. There will be some. But this problem is more of a terminology problem. Do you understand the terms being asked and how they're meant to fit together? So let's find out. What are some key things you need to notice from this problem itself so far? Area of a circle. Do we know the area of a circle formula? Okay. There's actually multiple area of a circle problems. So, for example, you probably grew up with this one, but there's also pi over 4d squared. There's also one relating to circumference, which is actually pretty weird, but I like. So why do we use this one? What is the key indication, besides the fact that it's a common one, what is the other key indication for why we use this specific formula? Yeah, it talks about drdt right here. It says specifically drdt, so it mentions a function with respect to r. That's a clue, trying to guide you in the right direction. So, what does it say? It says that A be the area of a circle of radius r that is changing with respect to time. Okay. If the r dt is constant, is the a dt constant? If I don't have an understanding of what these two pieces look like, well, I begin this problem by finding the r dt, finding the a dt. So my first step, I take this function and differentiate with respect to t. On the left-hand side, what's going to happen? dA dt. Think of a like x. The derivative of x would be 1, but because the dtt has to be x dt or dA dt. On the right-hand side, pi is constant. Is pi, boy? Is pi, my,
I said pi is.
I'm going to start putting a math problem where I'd say assume pi is constant. It's for you, Ricky. All right. Yes, pi is constant. Pi is like 3 or 7 or negative 12. So I always take derivative of the right-hand side. 2 pi r dr dt. Okay. So what does this say? It says, in the problem, dr dt is constant. Is dA dt constant? So what that means is, we have here a constant, there a constant, here a constant. Is this a constant? Thoughts? Is r constant? Good question. Is r constant? Is there any indication of the problem? R is changing with respect to time. So is r constant? So this one is not constant. So you have a constant times and that is not constant times another constant. Will this function be constant? Why not? R is changing. How can I make this better? Answer a little bit better? Instead of saying R, I could say radius is changing with respect to time. That'd make it even better. The first one's good. This is just a little better. Because I don't just say, hey, something that's obvious, I explain why I know that's obvious. R is changing. Yeah, of course it's changing. It's changing with respect to time, as indicated by the problem. It's more of a conceptual problem. I actually ask you to find the exact solution here, but to understand how the solution is going to interact with everything else. And I have to have a fundamental understanding of what's being said in the problem for 14. That R is changing with respect to time. That dRdt is a constant, that dAdt is checked to see if it's constant, because it could be or could not. Questions? You see? The radius of a sphere is increasing at a rate of 3 inches per minute. A. Find the rates of change of the volume when r equals 9 inches and r equals 36 inches. B. Explain why the rate of change of the volume of the sphere is not constant, even though dr dt is constant. Say what?
B is really easy to have to do.
You're right. You can solve B without doing anything else. It's a conceptual problem. Do you understand the picture of what this thing is doing? Okay? But if I want to do this problem, let's start at the beginning and talk about part A. Because there's some key things that can happen if you're not reading the problem correctly. So let's talk about it. Okay, first I'm going to start by drawing my picture. It's going to be a beautiful picture because I can't draw spheres. All right. Circle, line, R, and R is increasing at a rate of 3 inches per minute. So this is like R1, and then it gets, a little bigger. It comes like R2. Yeah, it's beautiful, I know. Eventually D2 shows up and we have a Star Wars party. Okay. Some things I know. Start talking to me. Or some things that if I don't know, I should probably find out what is this problem correctly. Volume of what?
Spheres.
What is the volume of a sphere formula? Do you remember?
4/3 pi r cubed.
4/3 pi r cubed. No, pi and r round, sir. Yeah, got it. Okay. This is V equals. That's needed for this problem. What does it tell us in the problem? Else.
R equals 9 and r.
So specifically we're looking at when r equals 9 and r equals 36. Okay, what else?
Increases at a rate of 3 inches per minute.
What increases?
The radius of the sphere.
The radius is increasing at a rate of 3 inches per minute. How do we turn that into something here on the board? What term have we talked about so far that deals with the rate of change of the radius? dRdt. How else can I figure that out? The units give it away. 3 inches, that's a radius number divided by time, dRdt. It's the changing radius over the changing time, dRdt. So what does it say? How can I put this on the board?
Hey, James, you got a copy?
What? You've got all the pieces. Tell me what to do. Take it through it. With respect to
Do you ever do?
dt. Because I could.
Yeah, that's what I meant.
You said it. You said it.
it wrong.
It was fine. It was fine. D over dt is correct. So I could take this with respect to r. I could take this with respect to t. I could take this with respect to v. There's a lot of things I could do or follow this because I've now opened a giant toolbox. Right? We have the standard functions, which apply when you have single variables of x, y, even r. We have more advanced ones that deal specifically when you have things like multiple variables where you're doing for one of them but not the other one. So you can do it with r and then have dv dr, or do it with v and have dr dv. But this one specifically tells me to use dr dt. because of what it says in the problem, 3 inches per minute. That is clearly d r dt, so I have to disrespect it t. So we're going to use d over dt. Let's do it. Here's my formula. Left hand side is dv dt. Right hand side. 4. You were close. Something is wrong here. Find it. R squared. Why is it r squared? It's a fact 1 from the power. Okay, what did the problem ask us to find? Find the rates of change of the volume. That's dv dt. Plug in 3 from here, and plug in your 9 and your 36 from there, and we'll have our 2 solutions for part A. Let's do it. Before I finish part A, does anybody notice something special about this formula? Perhaps it stands out as something else from geometry. 4 pi r squared is the surface area of a sphere. So fun facts, when it comes to 3D figures, if you ever have to for a competition perhaps, if you know all the volume formulas and ask for a surface area formula, there's a very simple way to do it. Take a derivative. Volume and surface area are intrinsically linked by a derivative. And we'll talk later on with integration about how to go backwards. If you have the surface area, you find the volume.
Yeah, they were even giving me a math help.
Never. All right. So we're going to follow the suggestions of our typical friend here. Casey said plug in the dr dt is 3. Ricky, you said plug in 9 and then plug in 36. Walk me through it. So the first part, at r equals 9, what is dv dt? Don't die over there. 4 pi 9 squared times 3. That's a good start. 4 pi 9 squared times 3. Okay, can you take it further? 12 times 81.
832?
Say again?
Isn't it 832? I'm trying to work on this math.
You're close. Should be 972.
972?
I think. Please check me.
Yeah, I got it. I got where that's up.
So think about this. The rate of change of the volume is this number. Put this as a decimal, please. Let me just get a calculator. 972 pi.
It's gonna be like
2800 something?
Yeah.
That's pretty close.
Uh,
What'd you get?
3,053.6280.
So, think about this. The volume is changing at a rate of 3,052 and decimals per minute. This states in the problem that this is in terms of minutes. That's a pretty big change when r is 9. So if you take a constantly flowing rate of radius change, that means the radius is growing at a constant rate. The volume is growing very quickly by comparison. Let's talk about what happened to 36. So same process. dv dt is equal to 4 pi 36 squared times 3. I don't know if I can do that.
12 times 20.
Hold on, wait. It's just this times 16. Right? Because the change there would be times by 16. 972 times 16. Yeah, that's not happening. Never. You have one for me?
15,552.
15,552 pi? Yeah, I totally did that in my head. Totally had that. So look at that. This is a consequence of the radius changing at a constant rate. Now, have you guys ever blown up a basketball or football? So what you're typically doing there is you're actually changing the volume at a constant rate. You're constantly pumping the same amount over time. So dV/dt would be the constant one, and the dr is changing at a different number. But think about this, like when the r is constant, the v is growing very quickly. When the v is constant, it actually works the opposite way. The r goes very slowly, and that makes sense again. You ever pumped up like a balloon, or you ever pumped up basketball? You put the same amount of air in, and the radius doesn't increase very much. It goes from here, that's the start, it goes whoop, and then it goes whoop, 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 whoop. The same amount of air is going into it, however the actual amount is changing, relatively small. Your dV/dt is constant, so the radius drops over time. Again, process. Picture is helpful, especially to get these key formulas that we may need. We have to develop an equation based on what we have, that we can then take the derivative of with respect to time in this case. I cannot stress this enough. Do not lose the other skills. On your final, you will have questions that are simple derivative questions. Take the derivative of f of x. You only do these kinds of problems when it mentions something like rates of change in volume with respect to time. If it just asks you for the rate of change of the radius, that's just dr by itself. ddr. So, questions? We got time for one more. Look at 16. Let's do 18. Oh, wait, sorry. B. Explain why the rate of change of the volume of the sphere is not constant, even though dr dt is constant. How would I explain that? I explained how the two relate to each other. I did not explain why one is constant and one isn't. As the radius increases?
Yeah, the radius is increasing at a rate which increases the volume of the sphere.
If it asks why dV/dt is changing in a weird way, it's helpful to look at dV/dt. What is in dV/dt? So you answered correctly. I just want to make sure to explain it fully. We have a constant, 4. Pi, constant. dr dt, constant. Times r squared, which is changing, as you said. Because the radius is changing, dV/dt must change too. One more time. Because the radius is changing, dV/dt must change too. Thereby it cannot be. 18. All edges of a cube are expanding at a rate of 6 centimeters per second. How fast is the volume changing when an edge is 2 centimeters? 10 centimeters. Couldn't be dr because we don't have a radius. The xct? Sure. If x is your side length. Sure. It's your picture. Draw it your way. Ready? I draw a picture. Cube. Yeah, it depends on what you call the side, right? I could call this X, I could call this S, I could call this J with a hat. Like, call whatever I want. Common one with square is side, so S. Other common one is L for length. X is common in general in math. Give it a name. Okay? I don't mean to sound like really condescending there, but it's one of those things that like it doesn't matter. It really doesn't. Just you gotta make a choice. You go. If you spend 30 seconds thinking of the name of this particular side, I'm gonna look at you and be like, that's 30 seconds you could have been doing this problem. Oh! Got it? Next. So, what do you want to call it? X. Love it.
dx dt equals 6.
So dx dt equals 6. When x equals 2 and x equals 10. All right. So far so good. Everything's been great. What? Very good. Volume equals x cubed. Take the derivative with respect to time. What gives away we should do it with respect to time? Centimeters per second. Centimeters per second. Centimeters is the distance. That's our x value, the distance. Seconds is time. So dx dt. Let's do it. Left hand side, what happens? Doesn't it sound fun when you say it? Right hand side. 3x squared. dx dt. So dv dt for this particular problem, and this is for this particular problem, it's defined by this set of information. So we'd have 3x squared times 6 or 18x squared. Now we plug in 2 first, what do we get? So at x equals 2, what happens to dv dt? 72. Fantastic. Okay. At 10. 1800. Alright, now I'm going to ask a question I've yet to ask yet. Because I think it's physics problems. I have to ask. What's the unit? Can't be centimeters per second.
No, centimeters.
Centimeters.
Centimeters cubed. Why is it centimeters cubed?
Because it's a cube.
Because it's a volume. It's a cube. We're asking how the volume is changing with respect to time. So the volume is a cube, the time is a second. So cubic centimeters per second. On the previous problem, 16, read the information. We got dv dt, it was equal to 15,552 pi. What? What will be the units on 16?
Cubic inch. No. Which one?
16.
Oh, cubic inches per minute.
Cubic inches per minute. Why do I know it's minute? Because that's minute in the problem. Yep. Believe it or not, most minutes point to these problems? Units. I will specifically write the instructions, include units. And you guys will be so excited, like, this math is hard. I got it! 72! Yes! And I'll be like, 1 point off.
Like that's as frustrating as like when you miss like you put plus or minus.
Hey, it's not my fault you didn't read the problem. Didn't do everything I asked you to.
Yeah.
If your parents say, hey, do these 4 things, you can 3 of them, you'll be like, I'm awesome. They're going to be like, this little piggy's like, oh. They were in trouble. Alright? In this case, these are mainly physics-based problems. Units will be included in every single one we do from now on. Alright? I strongly suggest for the ones we've already done some problems. Go back and find units too. Include those in there. Alright? Questions? We'll do some more of these tomorrow.
I didn't like these at first, but
They're different. And this opens a massive field. Because now we can literally do any equation between implicit differentiation, which allows us to do with a different variable, any variable we want. And now these rates of change formulas allow us to do it with respect to an unknown, an unquantifiable one, in this case t. T is nowhere in any of the equations we used today. T is in the background, like it is in a lot of physics. T just sits in the background doing its own thing. Huh? We have about a minute and a half left. No.
Yeah, I know. So we can like, because physics.
It's not what it means.
Have calculus and it's like.
So your 18 will be 6x squared.
If we take calculus, it's only good physics.
Well, no, it was still, it wasn't like calculus.
I'll tell you what. Fun fact.
With calculus to make it way easier.
In college, there are 2 freshman physics classes. Standard physics and calculus-based physics. Guess which one's fun?
Calculus.
Oh, yeah.
I already took.
Because they'll give you the formula and be like, hey, here's the distance formula, find the velocity, and be like,
Velocity is that.
take a derivative, solve it, plug it in, and everybody in the other class is like, plug in this formula, and you're like, okay, I can do it. Now, so Ricky asked a great question. He was talking about, if this is the volume of a cube, why isn't the surface area of the cube 3x squared? The surface area would actually be 6x squared. You add each side together. And it has to do with the fact that, in this case, the volume, if it was a perfectly spherical shape, would be 3x squared. But it's not true. In fact, have you guys ever asked the question, where did those formulas come from for things like the area of a circle?
I asked, but I never got an answer.
Calculus. Calculus. One of the first questions calculus actually was able to answer was the volume of a sphere. People theorized what it was, and they were right, they couldn't prove it. Newton came out and was like, I can prove it. Using this brand new technique I came out with, look at it, it's so shiny and pretty. And it worked. Where's the first Wednesday of the month here? What?